Although typically expensive, the purpose of our project was to design a lock-in amplifier at an undergraduate level. A lock-in amplifier is a highly sensitive voltmeter that locks into a specific frequency to detect a signal. What the lock-in amplifier does is multiply the target signal with a reference signal, where the input signal is a mix of the target signal and noise. The noise is represented by a Fourier series, and after applying trig identities, we can identify an equation with constant terms and cosine terms. Using a low-pass filter to eliminate noise, we can then extract the DC signal AB divided by 2, and we can solve for the unknown term A. For simplicity, we use the same input for the target and reference signal. For our circuit, we start with the summing stage. The high-pass filter eliminates DC offset from our function generator. This feeds into a voltage follower that adds the target signal and noise together to make our signal. This follower prevents noise from polluting our input signal. The two signals are then summed and divided by 2. This stage is used only for our test to generate the signal. Typically, you already have a signal with both the target signal and noise and are given a reference signal. Moving on to stage 2, the summing stage is followed by a pre-amplification stage. Because we set the target signal to a low frequency of 600 Hz, we use a low-pass filter to filter off higher frequencies. This feeds into an amplifier with variable gain. This is because we discovered that higher voltage inputs to multipliers gives more accurate results. For the same reason, the reference signal, taken from before the voltage follower, undergoes amplification with variable gain. On to stage 3, we now have both amplified signals that are fed into the multiplication stage. The multiplier multiplies the signals together, but inherently divides the input by 10. Moving on to the final stage, finally, the output from the multiplier is fed into the active low-pass filter. This removes the noise in both sine and cosine terms from equation 3, leaving us with a DC signal that can be used to solve for unknown term A. The output is monitored and measured by the oscilloscope. Since the gain for each stage is linear, we can calculate the overall circuit gain as a transfer function. By direct measurement, since the only variable is the resistors, we can calculate the gain for the entire circuit from the resistors. Starting from equation 3, we have the constant term AB divided by 2, multiplied by the gain from both stages, divided by 10 from the multiplier, divided by 2 from the summing stage, and divided by 4 because of the conversion from peak to amplitude. This will finally give us the output reading for the oscilloscope. For our input, we have 239 millivolts with a gain of 18.87 and 44.52 for both amplifiers respectively. From here, we can calculate the transfer function that gives us a V signal of 0.797 times V out. The target signal is 239 millivolts. We see a DC output. We test the DC output for different noise levels. Starting with the noise of 2 millivolts, we get a DC output reading of around 299 millivolts. For a noise of 24 volts, we get a DC output fluctuating around 300 millivolts, as DC output fluctuates more with higher noise. In this case, we take the average reading. Plugging the numbers into the transfer function, we see that both recovered signals are within 1% error, which is very good.